It now gives me great pleasure to introduce the moderator for today's first panel on weather and a co-organizer of today's event with our group, Dr. Christopher Thorncroft, Chair of the University at Albany's Department for Atmospheric and Environmental Sciences, who will in turn introduce his panelists. Chris?
Thank you, Rob. Good afternoon, everyone. First of all, I'd like to introduce the panel, and then the procedure here is we're going to give our 3 talks, and after that we'll have some Q&A. So I'm going to start off proceedings with a very kind of large-scale regional view of where we are in terms of extreme weather and climate change. And this will be followed by David Vallee. David Vallee is the NOAA's Northeast River, is the hydrologist in charge at the Northeast River Forecast Center. Has more than 27 years of experience working with flooding and everything water, and is going to be very busy tomorrow with the upcoming flood risks. His center is actually in charge of informing river flow, river flooding for most of New York and New England. This will be followed by the 3rd talk. This is going to be given by Thomas Blanchard. He works at the Department of Environmental Conservation, and he's the floodplain manager for Region 4. He has 29 years of experience of this problem, and we'll be talking much more about floodplains, laws. He's very experienced with the FEMA definitions, et cetera, dam safety. So that we're starting very large scale with me drilling down into more local scales as we move forward on the panel. So we're going to give the 3 talks. After that, we'll sit here and we'll take questions. So, extreme weather in New York State, past and future. Most people in this room are very familiar with this event. This was Hurricane Irene. We got 12-inch, sorry? So, 12-inch plus, I'll try and speak forward. 12-inch plus rainfalls. These are obviously some of the examples of the damage, the severe damage that was associated with the passage of Irene. And I'm sure many of the people in this room were kept up dealing with this event. Over the past, since 2006, there have been 19 disasters and emergencies declared for New York State by FEMA, and with a vast majority of those being associated with rainfall and flooding. 5 were associated with winter weather, snow, icing, etc. But of course, we are concerned with these events both in terms of the risk to property and life, but I'll also say in passing, variability in weather such as this and more generally impacts the economy of the state. And indeed, there was a study in the Bulletin of the American Meteorological Society a few years ago that showed that New York State is actually the most vulnerable state to the vagaries of weather variability. So highlighting the need to understand how weather variability is going to change, and ultimately, can we improve our ability to predict it. So I'm not going to shy away from the word climate change. So as background, I think it's important for us all to be aware of the global situation before we drill down into the local impacts. And so I'm going to give you some background on the global climate change. I hope you're familiar with this time series. This time series is of carbon dioxide at the Mauna Loa Observatory in Hawaii. And you can see, oops, wrong one. You can see very clearly that carbon dioxide is rising, okay? We're up, this last summer, we actually hit the 400 parts per million, which is kind of an interesting milestone for society to consider. Carbon dioxide is a greenhouse gas. We expect that to lead to a warming of the planet. And there's good science to support that. That's undebatable, undeniable. So where does this change in carbon dioxide fit in terms of the history of events? Over the last 800,000 years, this is where carbon dioxide has been oscillating around. We've been oscillating around 200 parts per million. We can get this information from observations from ice cores, mainly in Antarctica. So this is where we are in terms of natural variations in carbon dioxide. And this is where we're heading. So 400 parts per million, we're up here. So this current measure of carbon dioxide is unprecedented on the 800,000 year timescale. And man is responsible for that rise in carbon dioxide. As we go forward, carbon dioxide is continuing to increase, and we have a choice, or maybe we don't. in terms of a low emission scenario. Low emission scenarios, which are the most sort of conservative, if you like, in terms of increasing carbon dioxide, a challenge as our population continues to grow on this planet. It's going to take us to 550 parts per million by the end of the century. If we're more pessimistic, and many of us are, we'll be heading up to 900 parts per million by the end of the century. So this is quite a shocking time series that we need to be, which we all should be aware of. So what has that meant in terms of changes to global temperature? In terms of history, 1900 down here up to the present, we've increased the global mean temperature by about 1 degree on this scale. This is in Fahrenheit. So as we've increased carbon dioxide on the planet, there has been a general corresponding increase in the global mean temperature. These colored lines highlight potential futures for us. And we have low emission scenarios down here, high emission scenarios up here. So you kind of pick your poison depending on how much carbon dioxide is going to get reduced or not. And we've invested in, given the carbon dioxide released so far, we're pretty heavily invested in quite a lot more warming over the next decades. So these are the most technical slides I'm going to show you, and highlights the fact that we understand the culprit for this warming very well. The time series here, again, 1900 up to close to recent times, highlights model simulations of the planet, the global mean temperature. The black line is the observed temperature, which I just showed you, but blown up now. The red line highlights state-of-the-art climate models trying to replicate this mean temperature evolution, given natural forcings, given solar forcings, but most importantly, it includes the greenhouse gas changes as we know them. And I hope you agree that the black line and the red line are actually matching rather well. And that tells us that those models are capturing the basic physics that's going on in terms of describing that warming. So the good thing about having those models is that you can try and break down the causes of the warming. And the next slide is going to just show you what happens, and this is the blue line, if you take out the greenhouse gases that have been emitted by man. And hopefully you can see very clearly that we are now losing the warming signal. So the smoking gun here, of course, are the greenhouse gases provided by us. So this is the type of observational studies combined with modeling that allows the IPCC recently to make statements like this, and they make many strong statements like this, which are backed by a vast majority of the scientific community. Warming of the climate system is unequivocal, and since the 1950s, many of the observed changes are unprecedented over decades to millennia. The atmosphere and ocean have warmed, the amounts of snow and ice have diminished, sea level has risen, and the concentrations of greenhouse gases have increased. Now, if you're interested in knowing more details about the statements coming out of this process, I can direct you to such information. So that's the big picture. Let's now drill into sort of get close to these guys' interests in terms of regional climate change. And although we're mainly focused on upstate changes, I thought I'd highlight the sea level change in New York City. So anyone interested in flood risk, storm surge, clearly should take account of the sea level rise that's taken place not only on the planet, but also in the New York City region. And you can see that, sea level rise has risen by a foot or so over this time scale. This map shows you temperature change between, these are two periods, 1991 to 2011, minus that for the first 60 years of the 20th century. So red means it's got significantly warmer over most of the US. In the Northeast region, we are similarly colored red, so we've got 1 or 2 degree warming that is observed. Okay, this is something that's just a fact. So if we go forward to New York, where are we heading in terms of New York? Again, we have a choice, or maybe we don't have a choice in terms of where we're going to end up. Low emission scenarios, we might end up sort of Midwest, mid-coast, but we're heading, in terms of high emission scenarios, we're heading towards Georgia in terms of our temperature and climate. So this is a very interesting figure and extremely relevant to the discussion that's going to come after me. This shows you a map of observed changes in extreme rainfall. So this is like the top 1% or so in terms of extreme rainfall events. And the blue here, everywhere over US here, there's been an increased frequency of extreme rainfall events. I'm not talking about the mean here, I'm talking about the extreme rainfall. So the type of rainfall events that this audience is mostly concerned with. And it's kind of interesting, and maybe you already knew this, that the Northeast is coming out as the region of the US that has had the biggest change in increased intense rainfall. 74% increase in the number of extreme rainfall events between 1958 and 2011. What about the future? Again, there's doubts over the future in terms of projections, depending on how much greenhouse gases we are going to emit. The low emission scenario from the latest IPCC report is on the left. What I'm showing you here is the change in the 20-year event, such that on the left, with the low emission scenario, by the end of the century, we can expect the 20-year event to become twice as frequent. And if we go towards the high emission scenario, it'll be 4 times as frequent in the Northeast. So we've observed an increased change in the intense rainfall, the frequency of intense rainfall events. Projections are suggesting that that's likely to increase further. So it goes without saying that New Yorkers should be prepared for increased rainfall, increased intense rainfall events, and there's all sorts of issues that need to be discussed. This is like globally, this is really simplifying it. There's policy issues, there's building standards, there's infrastructure issues. I'm going to focus here actually on the weather forecasting issues. So dealing with this extreme rainfall event, and that's actually obviously useful for most people here. President Jones actually mentioned this project, this mitigation project that was announced by Governor Cuomo in January this year. So this is the Albany-led New York State early warning weather detection system. And I just wanted to highlight to you what this might look like. This is just a sort of a cartoon, really. We are pretty well off in some parts of the state in terms of observations, the so-called ASOS sites, or the red dots. The circles on this map are the proposed, rough locations for weather stations. Weather stations are going to be measuring rainfall, soil moisture, temperature, pressure, wind speed, soil temperature, radiation. Particularly important for this group in terms of forecasting rainfall and flood risk would be the rainfall and soil moisture. Currently, for example, in the Adirondacks, there are very few observations, and we are going to be including many more observations in that region, but across the whole state. Included in this activity will be the provision of quality control data for real-time decision-making, analyses, and improved short-range forecasts. So I'll summarize. The Northeast U.S. has experienced significant trends in temperature and intense rainfall over the past century, and especially in recent decades. Projections based on continued emissions of greenhouse gases tell us that we should expect these trends to continue. Expectations are for more frequent, intense rain events and associated flooding, which we were going to hear about in the next talk. This is a complete understatement. So efforts are needed to curb the emissions of greenhouse gases, but meanwhile, we are left dealing with the impacts of greenhouse gases in terms of the increased frequency of intense rainfall events. And so the Albany weather detection system is just one example of several projects that are going on out there in terms of dealing with this issue. And finally, I just want to say, I acknowledge some colleagues for some help with this presentation, but University of Albany, as President Jones just mentioned, has had a lot of investment in weather and climate researchers over the last few years. Coming up over the next year or two, we will reach a total of 30-plus faculty between atmospheric sciences, the Department of Atmospheric and Environmental Sciences, and the Atmospheric Science Research Center. So we have a huge expertise dealing with both the weather side of this problem, but also the climate side of this problem. And I'll thank you for your attention. So I'll now invite David Vallee up to the podium, and I'll see if I can get this fixed.
All right, thank you, Chris. Good afternoon, everyone. It's quite an honor for me to be here to participate in this very exciting venue. And a topic that's hit me close to home. Let's see. There we are. And that would be close to my home. I'll explain in a moment. The Northeast River Forecast Center is one of 13 river forecast centers nationwide whose mission is to develop and calibrate hydrologic and hydraulic models, including soil moisture, snowmelt modeling, et cetera, to then be able to produce forecasts and early warning for floods and for drought and for water supply. Here in New York State, we have some outstanding relationships. Federal partners include the Corps of Engineers and most notably the U.S. Geological Survey. Without those folks and their gauging networks, and the work that they do to maintain these sites, to maintain the rating relationships at the sites and the historical record, I quite frankly couldn't do my job of providing that early warning in the forecast for you. At the state level, we've had some tremendous relationships with folks in the Canal Corporation, with New York City DEP for water supply, et cetera. We've been blessed with tremendous partnerships over the years to help continue to expand our forecast services. So, what got me into the business of having some concern over the changing climate in your state and mine? I'm from Rhode Island originally and still live there. That's the face of climate change to me. That's my hometown of West Warwick, Rhode Island, where I never thought in my wildest dreams I would ever see the center of that town submerged under 12 feet of river water. To me, it's kind of become the poster child in a way, pardon the expression, but it's become that to me because it is very representative of what's going on throughout New York and New England. With a warming climate and bigger rain events and a wetter regime overall, in essence, Mother Nature is turning the spigot on with a little more vigor and a little more frequency. But we have a watershed like the Patuxent where we have a water supply facility at its headwaters, not built for flood control. It was designed to spill or to be full at the beginning of June. Through climate change, that reservoir that is at the headwaters of the Patuxent River is now spilling on March 1st. That's the sensible reality of what my river center is dealing with, because we're seeing changes in precipitation and temperature that is driving a change in river and stream behavior. We're first feeling it, or I am first seeing it in our modeling on the smaller watersheds, several hundred to less than 1,000 square miles. It's somewhat masked when you have larger rivers where you've got flood control because they are designed to control the flood flow, to kind of neuter the peak. But I'll guarantee you they're operating more frequently. So what I'd like to do is approach this from a practitioner standpoint. This is what I do for a living. Okay, my office has the responsibility of not only modeling these rivers and streams, getting the word out so that the local weather forecast offices like Ray O'Keefe and company here in the Albany area, so that they can get the warnings out to you folks in the EM communities and conduct those briefings. But coming at it from a practitioner standpoint, because we also have to forecast the rain and temperatures and the accumulation or melting of snow that drives the river response. So to me, it's all-inclusive, all-encompassing. I've got to deal with it from atmospheric to the hydrologic response. And what we've seen is simply an increased frequency of these big rainfall events. And I want to try to put from, again, my practitioner standpoint, I'm not a climate scientist. I don't try to play one on TV, okay? My job is providing you folks that early warning to the best of my ability. And what I'm seeing is the environment around us has changed. And the rivers that I forecast, that response is changing. In one way, I call this job security, but in another way, these events here really illustrate the changing climate throughout New York and New England. In this sequence of pictures, there are a couple of notable flood events. This is up in northern Maine. We happen to share forecast responsibility with the New Brunswick River Forecast and Watch Center on the St. John River. And you're seeing here their record flood back in 2008 from snowmelt. Not too early from this time of year, actually, a big April event. This flood event, which also did a number on upstate New York and the Adirondacks and the northern Hudson, has sort of been disguised or disappeared from the psyche because of Irene several months later. But keep in mind that this spring flood melt, kicked off by two really intense convective thunderstorm episodes, set the upper Hudson, the Adirondacks, and the Champlain Valley afire. And what you're seeing here is tremendous devastation just over the border on the Richelieu River, which flows out of Lake Champlain into Quebec province. This, of course, is the 2010 floods in my hometown, and this, of course, was just a heartbreaking devastation from so much rain during Tropical Storm Irene in the Schoharie Valley. So is there a common theme to why we think we're seeing what we're seeing? Again, from a practitioner standpoint, a couple of things that we know and that we have been observing is that our weather patterns have been displaying what we call more blockiness, a blocked up atmosphere. And what this does is it allows our storm systems to be a bit more slower moving. And that leads us into a regime where we either get one real big slow moving event that dumps large amounts of rain, or we get into a rut where we wind up with 2 or 3 or 4 consecutive rain events back to back to back. You look at the soils and the geography of our region, we're not built for that. Now you take the preponderance of evidence suggesting we've got a little bit more blockiness, and you look at the way the storms come at New York State and New England. Most often they're either coming up from the Gulf Coast and up the eastern seaboard or up the Hudson, or they're dropping down out of Canada and tapping Gulf moisture as they move down the St. Lawrence Seaway. In either case, these weather systems are interacting with what we call these tropical plumes of moisture. They had their origins in the deep tropics of the Atlantic and the Pacific coast and the Gulf of Mexico. So when we have weather systems approaching New York and New England, our weather systems have equal opportunity now to be tapping the Atlantic moisture plume or to be tapping the Gulf or Pacific plume, and in some cases, both of them. So if we have slower moving systems or a higher likelihood of getting these back-to-back events in close succession, our eyes then turn to what's going on with these moisture plumes. Well, these moisture plumes have been there since the planet began. What we are seeing now over the last 50 to 75 years from satellite imagery and observation is that these moisture plumes have more available water in them. And we believe that there is a connection to the warmer climate that is driving the availability of more moisture. So if you allow these systems to hit you more frequently or be a little bit more slower moving, they're going to have equal opportunity now to grab onto these moisture plumes, and as a result end up with that deep, anomalously moist air mass acting upon the state of New York and New England with greater frequency. And that is what we believe is driving us to this increased flood. Keep in mind that the soils we have a certain level of available space to hold that water and that moisture. We are most vulnerable here in New York State this time of year before we begin to green up and we see the grasses grow and the flowers bloom. And we're equally as in an uneasy situation if we've gotten into a wet pattern and then we get to early September or late August and we wind up with a visitor from the tropics, which was the basic setup that drove Irene up the coast, followed very quickly by Vallee just about a week later. So, what is it playing out to be like here in New York? Much like the rest of New England, we are seeing increased annual rainfall, annual total precipitation. We are seeing an increase in these localized, very heavy rainfall events, your 1-inch, 2-inch events in 24 hours, as an example. We are seeing warmer temperatures, that is a given, and I'll illustrate that to you. And in both cases, though, what I'm going to draw your attention to is not necessarily that we're kind of spiraling out of control to remarkable warmth, remarkable wetness, but it's really what we're not getting anymore that is equally as important, and you'll see what I mean momentarily. With respect to snowfall, I'll simply say if I could forecast for you a year in advance how the snow season will behave, we'd all be millionaires because it'd save every community in town that has to buy salt and sand a ton of money. But what we're seeing in this new regime is remarkable variation from season to season in the amount of snow that is falling on the region. Now, this is playing itself out into the design and into our infrastructure in the fact that based on the information from the Northeast Regional Climate Center, when you look back to the documents and the studies that were done in the 50s and early 60s, upon which we have built so much of our infrastructure around, right? The 24-hour, one-day rainfall, okay, your peak maximum rainfall, we're seeing shifts on the order of 1 to nearly 2 inches in that design storm. And that has a direct ramification on how we've built the infrastructure that carries the storm water and so on across and out of our cities and towns. And again, as I said before, the first port of call has really been these smaller watersheds, especially where there's been land use change and urbanization. So it's not just a climate thing that we're looking at. There really is a connection to what we've done with the place, if you will, in simple terms, where we sort of got this complex conglomeration of ingredients, how we've built out some of our communities, the amount of urbanization, the land use changes, and Mother Nature now doing things a little bit differently than she did when I was born back in the late 60s. So what I'd like to do, in the next 2 slides, we're going to step through a couple of snapshots, if you will. In the upper left, in this case, we're looking at temperature. The upper left is Central Park. The upper right is Buffalo, New York. The lower left is Albany, New York. And the far right is my poor attempt at snapshot in the Adirondacks, if you will, by using Burlington, Vermont as a proxy. Each dot on this graph represents the annual temperature for any given year from the early 1930s to 2013. In every single case, the green line, which is a very simplistic line of best fit, is pointing upward. It indicates warming. But what is fascinating to me is what's not in that orange circle. The cold years are gone. If you look at inside these circles, if the laser pointer hadn't died on me, I really could show it to you. What I've isolated there is the last 40 to 50 years. Look at the infrequent number of dots, especially in Central Park, Albany, and Burlington, Vermont, where we simply don't have cold years anymore, sustained cold. And I think it's no accident, through what Dr. Thorncroft just presented, why it is no accident that we are seeing our warmest years in the last 20 years. Now, there is quite a range of variability if we just use a very simplistic approach of a line of best fit to these points. You notice that the increase in degrees Fahrenheit per year range from as high as 103 years here in Albany, and part of that may be because of the sheltered valley location, to as high as a degree Fahrenheit every 29 years in Burlington, Vermont. That's remarkable. But to me, what strikes me is that we no longer have, with the frequency we did before, these prolonged cold periods, cold years. And that it is no accident that our warmest years in all four locations are clustered now in the last 20 to 25 years. Let's look at precipitation. So here, for each of the locations, we have our annual precipitation, rainfall and melted snow throughout the year. Again, applying a line of best fit, you see that every location is clearly going up. And in most cases, throughout the state of New York, we are increasing by the rate of 1 inch of rain every 6 to 9 years. That's a lot. But again, I point you to what we're not getting. Fascinating that we no longer have these dry years. Or at the very least, the frequency is far, far less than we did before. So if you think upon the soil structure and the ground beneath our feet, as my grandmother would say, the ground, the sponge as she is a wet, right? We're not losing that moisture like we used to. We're not having those prolonged periods of dry to get some of that moisture out. So we sort of have a half-baked environment or a primed environment with greater frequency because we're putting more precipitation down year by year. And likewise, it's no accident that so many of the wettest years have all occurred within the last 20 to 25 years. Remarkable signature across the entire state. I could show you this all the way to Caribou, Maine, and Rhode Island and Mass. It's the same basic flavor to what we are observing in our atmosphere and in our environment over the last 80 years. Again, Chris has already shown you that increase in that highest magnitude rainfall rates, and that to me is directly linked to the availability of moisture in these moisture plumes, which we know have a little bit more beef to them than they used to. Another way of looking at the sponge, if you will, is to look at the Palmer Drought Index. Now, this is used in the Midwest quite a bit, along with soil moisture indices, of course, to designate periods of drought or wet episodes. Oops. And what I want to draw your attention to here again is that left third of the graph from 1930 to 1970. All of the tan bars that you see there are representative of dry periods or drought periods. Notice the magnitude. The more negative the number, the more intense the drought. And the thicker that breadth of yellow, the longer the duration dry period. But what has happened to New York State in the last 40 years? These long-term droughts have all but disappeared. We now have these short, intense bursts of several months at a time where we're appreciably dry. But the general theme now is all green, which means very wet state and prolonged wetness. So if you've got all that moisture in the soil, we're not drying it out like we used to, we're getting systems that can act on these deep moisture plumes with more frequency, your whole system holistically is in a very primed state. And that has to result in an increased flood behavior. That doesn't mean everyone gets it every year. Different watersheds, different sizes, different makeup, different weather patterns are going to produce this type of increase in different places, different times. But the overall background state clearly is warmer, wetter, and the dry periods are much shorter and much less intense than they used to be. Another way of looking at this from a design standpoint, as I had mentioned earlier, the Northeast Regional Climate Center out at Cornell University has updated the old TP41, which was developed back in 1960, which has been the design documents for so much of our infrastructure, from culway design, the capacities of spillways, and so on. And what they illustrate for us nowadays is that through much of New York, from western New York The new 24-hour rainfall event that has a 1% chance of happening in any given day, or what some still refer to as the 100-year event, okay, was an event over 24 hours of generally 5 to 5.5 inches. Today is now between 5.5 and 6 inches. And you notice that as you get down to the southeast part of the state, that new 24-hour rainfall event is somewhere on the order of 8.5 to 9 inches. So that's a 24-hour total of rainfall that has a 1% chance of happening any day of the year. The issue we're running into, especially in some of the urbanized, smaller metropolitan corridors, is what we designed for was this: a 6 or 7 inch event, not a 9 inch event. So parts of New York State, much like much of coastal New England, have actually experienced a shift of anywhere from 1 inch to 1.5 inches in some coastal areas, nearly 2 inches in what we used to think was the 1% or 100-year rain event for 24 hours. That's a significant shift. And we believe that that is having an impact on some of these older communities where we've had urbanization and land use change, where the infrastructure simply isn't there to carry that kind of capacity, that volume of water. And that's the reality of what we're seeing in some of our communities. So to end up, what is this looking like flood frequency-wise? We're seeing a changing behavior in these smaller watersheds, especially where it's been coupled with land use and urbanization. But again, it's not just climate change. It really is a total conglomeration of everything that we have done and how we've built out in an environment now where we are simply wetter and warmer. So, courtesy of the U.S. Geological Survey's historical data, my basin focal points have developed these graphics which simply illustrate for each year, calendar year, the peak flood, and if there were more than one flood, the numbers of floods in a given year. The shading on each bar represents its magnitude, minor, moderate, major, based on the Weather Service's flood elevations at these sites. And you can see that starting here, looking at Wappingers Falls down in the southeast part of the state, you'll notice that there has been flooding with some frequency since the gauge was put in back in 1929. But the thing that jumps out to me is in the last 15 years or so, this increase, not only in magnitude, but in the numbers of floods in a given year. So we're seeing these variations now beginning to play out on some of the locations that I forecast for and that we model for. We're seeing a different response, and we're seeing things like, in this case, the preponderance now of having multiple floods in a year and multiple floods of moderate or major severity. If we move to Prattsville, if you just draw a line from about 1970 or so, look at the frequency of flooding. Now, granted, many of them were at major flood, but far less frequent prior to 1970 than the incredible frequency we have now. And also notice, again, that shift to having more than one flood in a year of moderate or major intensity. So again, just a small snapshot, one example on another stream that my center is responsible for, where we believe we are seeing this changing behavior as a result of the wetter regime. If we move out west along the Mohawk and we go to West Canada Creek, again, there's fairly frequent history of flooding in this watershed, clearly back to the early 1920s. But again, in the last 40 years or so, we're seeing this increased frequency of intense, moderate to major floods, if not multiple floods in a given year. And if we go way out west, the Black Creek in Churchville, New York, again, maybe not as pronounced, but there still is an increase in frequency, if not an increase in frequency of more than one event in a given year. And lastly, Watertown. Here, I think it is clear, just a much greater frequency of floods from year to year than what we were seeing back in the 30s, 40s, 50s, and 60s. And again, through a lot of the research, there seems to be a turning point somewhere in the mid-70s, early to mid-1970s, where so much of this began to change. So in summary, Northeast New York, in our opinion, from a River Forecast Center standpoint, things are a little bit different. We are seeing rain events with greater frequency and intensity than we used to, and we're seeing that rainfall and the general wetter condition throughout the course of the year being more prevalent and changing the way that we are modeling our rivers and streams because of this increased flood behavior. Thus far, much of what we've seen have been on the somewhat smaller watersheds, but I think it's only a matter of time before we begin to see the same type of behavior spread its way out. And it has far-reaching implications with you folks on the ground sure well know, just having to deal with some of these horrific floods in the last 10 years. It deals with everything from our floodplain and land management use to the infrastructure to how we design things and what we need to be designing for, and of course, how it plays out in how we insure our properties and what mitigative steps we wish to invest in to try to reduce the losses the next time we have a flood in the community. And I'll leave you with this last slide. This is simply a couple of websites that NOAA has, or some of our partners, such as northeastclimate.org. Resources to you in the communities that you can leverage, either for just day-to-day monitoring or certainly for a wealth of information, especially on State of the Coast and the climate.gov site for future reference for the work you may be doing in your communities. Thank you.
Thank you, David. So now I'll invite to the podium Thomas Blanchard. Again, to remind you, he's from the Department of Environmental Conservation and now leads, this last talk leads very nicely into the floodplain discussion. That's what it was. This isn't really working, I don't think.
Hi, thanks. Chris moved things from the global level down to the northeast level, and now I'm going down to basically the backyard. Problem, I've got one set of slides here and one set up there. Not going to work out. Here's the statistics, and people are probably pretty familiar about it. But the thing I'd like to really point out is at the bottom, flooding is one disaster that can be mapped. And that's a little bit unique. You can't map a tornado. I can't tell you with any kind of certainty which house is going to be blown up in Kansas next week. But we do have floodplain maps. In 1968, the National Flood Insurance Program was enacted, and basically the idea behind that program was to identify flood-prone areas, establish flood risk zones, require new and substantially improved buildings to be constructed in a way that minimizes flood standards. And the whole idea was to transfer the cost of the loss of the cost of the flood losses from the taxpayer to the people that actually live in the floodplain. And here's the first generation maps that came out of that 1968 Act. There wasn't a whole lot of money involved in that program, and it wasn't until after 1972 with Hurricane Agnes that we suddenly got some money to do some better mapping. In 1973, we decided to accelerate the issuance of flood insurance studies, and we started notifying flood-prone communities that you do have floodplains and should take action. There was a mandatory purchase for flood insurance for structures that were funded by the FDIC, for example. And in order to get flood insurance in your community, you had to participate in the program. So the mapping comes out, it's a little bit better, maybe. And from about 1973 or so, things just kind of moved along, and we have several different generations of mapping. These maps were around prior to about 1986, and this is just a floodplain map. How many people out there know what year your floodplain maps or what generation they are? Any idea? You've got the new ones, I know, but here, if your floodplain regulations are prior to 1987, you actually had two maps. This was the floodplain map, and this was the floodway map. The floodway is an area you don't want to build in because it's got high velocity waters, and that's the white area between the two shaded areas. That got to be confusing when I started on this program just a few years ago. It was not uncommon to have a floodplain manager very familiar with his floodplain maps, but have no idea where his floodway maps were. So we changed that. And now we put both maps together on one. What a revolutionary idea. We have floodway map as the crossed hatched area. Again, that's the area where very restricted building. It's got the high velocity water, someplace you really don't want to be during a flood. Along comes the great floods of the Mississippi, Great Flood of the Mississippi, something like that. It's been a while. So the program gets expanded again. Now there's penalties for noncompliance, and one of the problems they found coming out of that flood was a lot of people knew they were in a floodplain but never bothered to buy flood insurance. So now they've established lender penalties. Remember from the earlier slides that flood insurance was mandatory. It's just that there wasn't anybody making anybody get that flood insurance. Flood disaster assistance became required a flood insurance policy if you receive disaster assistance. Now we move forward a few more years and we start getting a little fancy with our toys. And we have LIDAR, and the FEMA standard is plus or minus a foot. From what I understand, we can get down to about 4 inches. It's just a matter of computing power to be able to analyze all that data. The end result is we develop a 2-foot contour, and we have to supplement our LIDAR with on-the-ground surveys. As far as I know, I think New York State was one of the first states to actually use true digital floodplain maps using this method with LIDAR and on-the-ground surveying. That was done in Schoharie County in 2000-ish. The new maps came out in 2004, but it took 4 or 5 years to do the peer review because it was such new technology. And this is what we came up with. This happens to be in Prattsville, but that's the product, that's the end product. You have your digital map, you've got your elevations, and you've got your cross sections, lots of information there. The components of a DFIRM, or digital flood insurance rate map, so you have your base map, you have your topographic data, flood hazard theme, and the great part about this method of mapping is you can take it and add layers and take layers out. When I do this for my job, I often have a layer in there for stream classification because of other regulations. And I have another layer in there for wetlands, because believe it or not, wetlands and floodplains tend to be in the same place. The thing you can also do is you can add your property data, real property service information into that layer of map. And as climate changes or your data set changes, you can go in and change one layer rather than remapping the whole process. If you want to change just the hydrology layer, you can change just that layer. If you get new aerial photography, you can change that layer and just update the single layer rather than the whole product. So what you come up with is one of the uses for this is we have a community here, and in the red, I've highlighted every piece of property that touches a floodplain. So right away, from an emergency management point of view, you know how many structures in your community, more or less, are flood prone. Of more interest, perhaps, is now you can get down onto the level and check it to see about critical facilities. And although this is just a straight up property map with a floodplain, you can add in the aerial photography and start looking on a more closely or more closer basis. You can, I guess this doesn't work. Over in this corner, more or less, you can see a large building that is touching the floodplain, but not quite in the floodplain. So now you know that that building, although in general the property is in the floodplain, the structure itself is not. There are other structures that are clearly in the floodplain. Those are not where you want to put your evacuation centers. Probably not a good place to put your fire department. Here's another one. This is in Freeport. The blue line is the 100-year floodplain, or 1% floodplain. And this is what Freeport looked like after Hurricane Sandy. It's pretty remarkable how close the floodplain is to the actual inundation area. And to give you an idea, it's not a perfect world. If you went further west towards Staten Island and Queens, the flood was actually greater than the floodplain. If you went further east, they were, according to one of the homeowners, the flood maps were spot on. And here's a view of Prattsville. Again, you've got your floodplain map. And then the next map is Google Earth imagery. And I don't know if you can see it from out there, but the browner areas along the river and up in the fields, that's the area that was inundated during Hurricane Irene. And if you compare the two, you can see that it's fairly close, that the floodplain map and the floodplain or in flood from Irene, we're actually fairly close. What the floodplain map doesn't show you is that they had 17 or 18 inches of rain up in Wyndham, and that instead of the flood being 2 feet deep, it was closer to 6 or 8 feet deep for some of these folks. That's the wonderful thing you can do with digital flood maps. The unfortunate part is the dark green is where we have digital products available. The blue, or the light blue, is yet to come. So you can see the western part of the state and the Adirondacks, digital products are few and far between. On the other hand, in the green areas, that's mostly where the population of the state is. So a lot of people are aware of their hazard. So the maps are a vital tool for floodplain management, for sustainable community development, for emergency management. Again, use those maps for personal protection and for property protection. Nobody should be surprised if they live in a floodplain that they got flooded. We can use it for flood mitigation planning, which most of you folks are probably familiar with. Trying to get coordinated. Flood warning and response, and construction standards. New York State requires a 2-foot freeboard elevation in their building code. It's the only state in the union that does that right now. And we can use the flood insurance maps for flood rating. This is the value of elevation. You can see a house that's elevated out of the BFE, the house closest to me, we'll see about $427 a year for a flood insurance policy. On the other hand, the policy on the far end of the screen is running around $9,500 a year because they're a couple of feet below the base flood elevation. So building higher is better. And we get all kinds of static about doing that. It's going to make the house look ugly and all that kind of thing. Here's an example of one homeowner who begrudgingly accepted the building standards and finally did elevate his house. And the neighborhood took on 4 feet of water. It reached the bottom of the top step. So, you know, it was right coming up the front step. No water in his house. He was happy. When I toured duty around Long Island, one of the building inspectors was constantly being hugged by people who formerly had lawyers ready to go and hang him, kind of thing. So when the code enforcement actually works well, there's a lot of benefit to it. Here's an example of a house being elevated. And you can see that blue house is a 2-story structure, and they're elevating it almost 1 story to get it out of harm's way. Here's an example of Myers Grove. I was down there around the 2002, I think it was, when that flood came in. The house that's there now was originally wiped out during the flood. When they rebuilt, they built back elevated and stayed dry. Here's Riverview Manor for those folks in the Schenectady, town of Glen area. This guy, his consultant came out and talked to me about how to build this. I recommended 2 feet above base flood elevation. Gave me a hard time about it until I explained the benefits from the insurance end of it. And he stayed high and dry. The only casualty was a catering truck his daughter left in the parking lot in the lower end of the parking lot. Didn't work out so well. So here's some of the challenges of the NFIP. Future conditions mapping, risky development, and recovery is well funded, but mitigation is not. So what I like to say is that the floodplain maps are out there. They are available now, and they're a tool that should be used for all the problems that they have. It's a lot better than nothing. So that's about it. Here's more information.